going to talk about very elegant criteria that guarantees a sequence convergence, and it has to do in monotone sequence. What is monotone sequence? Monotonic sequence is a sequence that always moving one direction, and it can be arrow above, this is the increasing sequence, or it can be arrow below, then this is called decreasing sequence. When a sequence either increasing or decreasing, then the sequence is called monotonic sequence. Okay, alright. What is the definition of increasing sequence? Let's see. A sequence is increasing if the next term is always bigger than previous term. That means an plus 1 greater than equal to an for all n belongs to natural number. Okay? This is the increasing sequence, which denoted as this arrow. Okay? And a sequence is decreasing sequence which denoted as this arrow if the next term is always less than previous term. That means an plus 1 less than equal to an for all n belongs to natural number. Okay? This is called decreasing sequence. Are you getting my point? Okay. Let's see graphical representation of sequence. Here you can see the element of the sequence always going up. So this is a monotonic increasing sequence. Okay, all right. And what is the graph of monotonic decreasing sequence? This is the monotonic decreasing sequence, because all term always going below. Okay, all right. Now let's see this sequence. Is this sequence is monotonic sequence? Notice that this sequence actually at first going up, then going down, then going up, then also going down. Okay? That means it is not increasing long time or not decreasing in long time. So this sequence is not monotonic sequence. Are you getting my point? Okay. My next proposition is a bounded sequence. A sequence AN is bounded sequence if there exists a positive number m such that absolute value of AN less than equal to m for all n. That means each term of the sequence is less than equal to m. Okay? Alright. Then we have a theorem. Every bounded monotonic sequence is convergent. That means if a sequence has two properties, bounded and monotonic, then the sequence must be convergent. And obviously, if a sequence monotonic, that means the sequence either increasing or decreasing. Let's see the graph. Suppose the sequence is increasing sequence. That means it's go above, and since the sequence is bounded, that means it has a bound m. Then this m actually has to force the sequence converges. Since the sequence bounded by m, that means this sequence cannot go above this bound. Okay? And since the sequence is monotonic, then this sequence cannot decreasing anymore, because this I consider this is increasing sequence. Then they will stay slowly increasing or remaining same when they actually reach the bound. Okay? Alright. And from this graph, it is clear it converges to upper bound m. Are you getting my point? Alright. It does not mean sequence has converged m. It can converge something smaller m, and this is L and this is the I consider the bound m. Okay? Let's prove these properties. It can convert something smaller than m. Proof. Let AN be increasing bounded above sequence. Okay? And consider the set A equal to AN such that n belongs to natural number. Okay? And this set is the set of all terms of the sequence. Clearly, it is non-empty and bounded above. So, it has a supremum. And by LUV properties, it must have supremum. Okay, let L equal to supremum of the set A. Are you getting my point? Okay. Now my goal, we have to prove L equal to limit n tends to infinity an. This is my proof. Okay. For this purpose, I fix arbitrary epsilon greater than 0. By the definition of the supremum, there exists n naught belongs to natural number such that L minus epsilon strictly less than a n naught. Okay, that means this is L, this is L minus epsilon, and this is a n naught, and this is true by the definition of the supremum. Now I take this value n naught. Now I take this value n naught. Okay, fix n belongs to natural number and assume n greater than equal to n naught. I need to show an strictly less than L plus epsilon and strictly greater than L minus epsilon. Okay, since by this picture, since L minus epsilon strictly less than n naught, and since the sequence is increasing, then let this is n naught, n naught always less than equal to an. Okay, and by the definition of supremum, an less than L, and I put this inequality, L minus epsilon strictly less than an naught, strictly less than an, strictly less than equal to L, strictly less than L plus epsilon. From this inequality, we can write easily an lies L plus epsilon, L minus epsilon, and this is the definition of limit. So from this inequality, here for all n greater than equal to n naught, we can write limit n tends to infinity an equal to L, and our proof has done. Okay, all right. Now see decreasing sequence. This is a decreasing sequence and it crosses the axis and become negative. Okay, and it keeps going down, down and down. Okay? And it is bounded by capital M, bounded above by, and bounded below by capital minus M. Okay? Since it is decreasing sequence, it is converges to M. Obviously, it can converges to very close to M, but it would be the value larger than M, and you know the fact. Okay? Alright. Monotone convergence theorem is one of the most convergence tools, and we can use to establish some sequence of convergence without having to definition of convergent. That means when a sequence is monotonic, in other words, it is either increasing or decreasing and bounded, then the sequence must be convergence. That means for monotone increasing sequence, it is bounded above and bounded below for monotone decreasing sequence. Then the sequence would be automatically convergence. Are you getting my point? Okay. Let's look an example when a sequence converging using monotone convergence theorem. Let's see the one example. Prove that the sequence defined by S1 equal to 1 and Sn plus 1 equal to square root of 1 plus Sn is convergent. Here, every term is produced from the previous by taking and adding 1, then taking square root. Okay? At first, we have to verify monotonic. Look the sequence S1 equal to 1. So here S1 equal to 1 and S2 equal to square root of 1 plus 1 equal to square root of 2, which is equal to 1.414. Okay. S3 equal to square root of 1 plus previous term, which is equal to square root of 2. Then the value will be 1.514. Similarly, S4 1.598, so on. This is the first term, this is second term, this is third term, this is fourth term. Fourth term of the sequence is increasing pattern. So, from that we can tell the sequence is monotonic. Okay? Now, I will prove it by induction. Proof. We have to prove SON plus 1 strictly greater than Sn for all n. When n equal to 1, then given S1 equal to 1. If we put 1, then S2 equal to square root of 2, who is greater than 1. So this is true. For this is true for n equal to 1. Okay? Let us assume this relation is true for this relation is true for n. That means Sn plus 1 strictly greater than Sn. Okay. Now we have to prove by induction this relation holds for n plus 1. Okay. Then I will get Sn plus 1 equal to square root of 1 plus, sorry, here not 1, Sn plus 2 equal to square root of 1 plus Sn plus 1. Then from this line, since Sn plus 1 strictly greater than Sn, I have assumed it. From this line we can write strictly greater than 1 plus Sn. And square root of 1 plus Sn means Sn plus 1. That means Sn plus 2 greater than Sn plus 1. So it is true for n plus 1. Then I can write by induction Sn plus 1 strictly greater than Sn for all n. Okay? Alright. Now we have to prove Sn is bounded. Look at first few terms. S1 equal to 1, S2 equal to 1.414, S3 equal to 1.514, S4 equal to 1.598. Okay. So from this line we can tell all these terms less than about 2. So Sn is bounded above by 2. Okay. Alright. Actually we have to prove Sn, absolute value of Sn less than equal to 2 for all n. Okay. So for this we use induction method. By induction, let n equal to 1. Given in question S1 equal to 1. Okay. So absolute value of S1 equal to 1, which always less than equal to 2. Okay. Now we consider, assume this is true for n. Let absolute value of Sn less than equal to true. By induction, we need to prove this is true for n plus 1. Okay. absolute value of Sn plus 1 equal to Sn plus 1. By the question, this is 1 Sn plus 1 equal to square root of 1 plus Sn, which is equal to square root of 1 plus Sn. Since Sn is bounded above by 2, that means this is less than equal to 1 plus 2. Since all term of the sequence less than 2. Okay. This is less than equal to square root of 3, which is always less than equal to square root of 4, which is less than equal to 2. That means by induction this is true for n plus 1. So we can write by induction Sn less than equal to 2 for all n. Okay, alright. Since the sequence both monotonic and bounded, then by monotone convergent theorem we can tell the sequence is convergent. Okay, let's verify the limit. Event sequence is defined as Sn plus 1 equal to square root of 1 plus Sn. Okay. If L equal to limit n tends to infinity Sn, then taking the limit both sides of the equation, we can get limit n tends to infinity Sn plus 1 equal to limit n tends to infinity square root of 1 plus Sn. Okay. Assume this value equal to L, then this is equal to L, and this value will be equal to 1 plus square root of 1 plus L. From this line, we can write L square minus 1 minus L equal to 0. That imply L equal to 1 plus minus square root of 5 over 2. Since given each term of the sequence is positive, so by the monotonicity we can write L will be greater than 0. So the value of the L always 1 plus square root of 5 over 2. Okay, alright. That means this is the limit of the convergent theorem. We can use here epsilon delta definition, but we can also use any convergence of a sequence by this monotone convergent theorem. Okay, all right.